Alright, this is how to decode a data matrix by hand. The real short of it is, this is what a data matrix looks like right here. And it is broken up into bytes in this kind of fashion. And each byte equals something, which -1 is an ASCII value, unless it's a pair, which it can mean two numbers, and that's the short of it. It has about, I don't know, a 14 by 14 here that I have has 18 bytes worth of data into it, but it only uses half. Okay, so that's the short of it. That's how you decode a data matrix in less than a minute. Anyways, now let me show you how to decode a data matrix by hand and all the steps behind it. So the first thing I'll show you here is this data matrix, and you can see it as a capital ABC, then a lowercase abc, and then 1, 2, 3. Now this is a 14 by 14 size data matrix, and 14 is the number of cells, which is the number of pixels, if you will. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then 14 down. So the basics behind a data matrix is that it has a border, a solid black line on the left and bottom side, a dotted black line on the right and upper side of it. Now it's broken up into these L-shaped regions here, and these L-shaped regions have a pretty basic what do I want to say to this? They have a pretty basic shape to them. So let me just do this, and I'll show you. This is the real short of it. It goes in this kind of pattern where it's 128, 64, 32, 16, 8, 4, 2, and 1. And if these cells, these little dots are on, then that is that byte's worth turned on. For instance, if this guy, I'm going to use black to show it, we're on, and this guy we're on, then that means I'm going to do 64 plus 2. And so let's say 64 plus 2 equals, of course that's 66, but because the data matrix has 3 different types of what the data can mean, or really the basics of it, is that it either can mean an ASCII value, and this is an ASCII chart, and this is going to be the values of between 1 through 127, or really 128 if you're going through 0 through 127 or 1 through 128, but in this case we're going to do 1 through 128 kind of thing. So anyhow, let's see, what was my value again? It was 66, and -1 gives us 65, and 65 in ASCII, go up to our chart here, is a capital A. So that's how the L thing works. Now this isn't the data matrix that I'm going to show you how to decode. This is just an example how to use the L bracket. So now we got to fill in the rest of these guys here, and it kind of looks, let's see if I can find a better picture. No, I suck at this. Alright, well let's fill this thing out by hand. You're going to go for like a couple different colors here. Blue. So on the top corner of the data matrix, it's going to look like this every single size you have. And then from there, you're going to have a different size data matrix, and each one of them are going to look slightly different in how they're laid out. But each of them have this kind of basic thing where it's just laid out like this. Now the extra ones on the sides here are still bytes, but they're laid out oddly different. So turning this guy back to blue and this guy back to blue, let's go through here and figure this out. Now you see the L bracket here, and you see how they kind of all fit within each other in this kind of fashion. Now the first thing you want to do is you want to find all the complete L brackets that you can that'll fit. Obviously I can't fit one here because it's only it only has 2 spaces wide. I need 3. So what do I do with this data? Well, the first thing you're going to do is start here, and you're going to create a new one as if there were one there. However, there isn't, but we're going to kind of create it like it were. And then this guy, as if there were one there, we're going to give it, you know, a partial size there. And then there's one over here. He goes there. And the reason that we're doing this is essentially we're wrapping the data around the border of the data matrix. So anyhow, let's see if we clear these things here. I want to show you the order of bytes that this all goes in. But let me finish this real quick. Okay. Alright, a green there. And orange there. And finally, I'll leave that last one white because that one's special. It's special in a terrible, terrible way. Anyhow, these, let's break it down like this with the grid. So this is the byte that we, or this is the order of bytes. Man, this is so hard to explain. And each one of these has a corner here of our L bracket. We're looking at the lower right hand portion of it, and we're going to put a little X there in every single one of them. And the idea is that we go from the one standard one that's always going to be here in the corner. That's called that's going to be our chunk number 2. Now chunk number 1 starts down here because technically if it were there, it actually wraps around over here and is on this side. Remember how I told you the data wraps around? Since I have 2 here, I have the matching 6 over here. So anyways, byte 1 starts here, goes up to 2, and then up to 3. And 3 wraps around down here for the remaining 5 that's missing. Being it has 3 here, so a total of 8, so that makes sense. So then it comes down here to 4, then we go to 5, 6, and you can see I'm hitting the X's on each one of these guys, 7. And then we have that special guy down here, number 8. And 8 is also up here. 8 is this corner guy, and the corner guy is very special. If we go to Wikipedia and we search for data matrices, you'll see this nice screen like this, and it has, this is a great reference to I learned this. I have a buddy of mine named Sean who also taught me this as well. But anyhow, the corner byte is either going to be one of 4 different cases. In this case, we're looking at case number 1, where it has the kind of upside down L and 3 of them down here. That's the case we're looking into with this one, where it has 3 down at the bottom and an upside down L over here. And you'll get different cases based on the different size data matrix you're working with, be it 10 by 10 up to 20 by 20. And so you can see on the Wikipedia site, maybe a better representation of the way I did it, is that you can see the little red dot in that bottom right corner of the L bracketed byte, and it goes in a pattern such as this. Wikipedia is a great reference if you want to relearn how to do this again, but hopefully this video is a great starter for you, although it may not be. So anyways, you'll notice that there's like 18, or yeah, 18, 17, who cares? There's a bunch of byte sections here. Okay, I show 18. But anyhow, there's all these byte sections, but really only 8 of these 18 are used for data. The other 10 are for error correction. Now, the error correction is something called Reed-Solomon error correction, and I'm not going to bother trying to teach you that because I don't know what I'm looking at. I mean, this is Reed-Solomon. This is a bunch of, I don't know what I'm looking at. I'm a programmer and nowhere near a mathematician. I mean, look at this. No, that's silly. Forget this mess. Back to the simple things like ASCII. So anyhow, I remember how I told you that this was byte 1 and it wrapped around down here. So this is the data matrix that I've decided to decode. And it is, again, capital ABC, then lowercase abc, and then 1, 2, 3. So byte number 1 here is, I like to call them chunks, because it doesn't necessarily equal the byte, because in case of numbers, it could equal 2 bytes worth of data. And I'll get to that in a bit when I hit the 1 and 2 and 3. So byte, or chunk number 1 here, being that we always start beneath the first completed one. The first completed one is always going to be 2, and the first one is going to start here. So remember that over here, I'll show you chunk number 2, which is the whole one. I got 128, 64, 32, 16, 18, 4, 2, and 1. It's the same pattern, just wrapped around for byte number 1. So I got 128 and 64, then 32, 16, 8, 4, 2, and 1. Now I've kind of darkened the cells here where they're filled out on this guy. So 64 and 2 are highlighted. So 64 plus 2 is 66. Minus 1 is 65. And going to our ASCII chart, which you can search ASCII, it's ASCII, and you pull up a whole bunch of ASCII charts. They're all over the place. But anyways, 65, if you go to our decimal thing here, 65 is a capital A. So there's the first character of our barcode, capital A. Nice. Well, you can kind of see where this is going to go from here. Our second byte has 64, 2, and 1 highlighted, are filled in with black in our data matrix here. That is 67. Minus 1 is 66. 1 more than 65. It's a capital B. And we can go back to our ASCII chart here and see 66 is indeed a capital B. So, continuing on down the line, the next one has 64, and this one's wrapped vertically. So it's just, 128, 64, 32, 16, 8, then 4, 2, and 1. Gives us 64 plus 4, 68, minus 1, because that's just how the data matrix does it. The ASCII values are always just 1 more than they should be, so you just subtract 1 to get the full ASCII value. 67. Being, again, 1 more than 66 is the next character down, C. And so in the ASCII chart, you have capital letters and you have lowercase letters, and you have a couple other things like numbers, and you got symbols, and you have a couple other like serial type commands like character return as if you were to hit the enter bar, or tab, or something along that lines. Anyways, the next character we're going to be looking for is a 97 for a lowercase a. So coming back to this, we have, let's see here, starting here, 64 plus 32 plus 2 is 98, minus 91, there's that 97, gives us our lowercase a. Now the same thing here for chunk number 5, 64, 32, 2, and 1 equals 99, minus 1 is 98, that is lowercase b. Now for C, you get the picture. For chunk number 7, now this one does wrap around again. But this one is special, as in it is not an ASCII character. The thing about DataMatrix is very, very smart, whoever came up with this, is that if there are 2 numbers next to each other, it displays them above 130, and you just subtract 130 to get those 2 characters. It's just really quite ingenious. So here's the thing, 128, and it wraps around and comes up a little bit, and then you go 64, and 32, 16, 8, 2, 4, 2, 1. So we got 128, 4, 8, and 2 equals 142. So the thing is, now we're going to subtract 130, which gives us 12. What are our next 2 characters? 1 and 2. Pretty stinking smart, isn't it? So if you had, say, 195 minus 130, 195 minus 130 is 65, so the next 2 characters would then be 6 and 5. Pretty stinking smart. I like the way they did that. Now, this is only for digit pairs, and so our final character is 3. Now, in this case, this is this weird thing where I had to go to Wikipedia to get... Oh, get out of here, Reed Solomon. I had to go to Wikipedia to get the case, and eventually, if you want to do these things by hand, you'll probably have to memorize these 4 little cases here, which aren't too hard. I mean, I wanted to learn the data matrix because it's like a puzzle, and I love puzzles. Of course, I do code, so puzzles are my thing. Code is a big puzzle. So anyhow, you have to get the bit positions off this guy. So this being 1, this being 2, 4, 8, 16, 32, 64, and 128. So coming back to this guy, We got 32, 16, and 4, which gives us a total of 52. That is less than 130, so we know it's an ASCII character. And that is 51. So 51 is, drumroll please, an ASCII number 3. So that is the last character right there. It uses ASCII versus, instead of the pairs, because there's only the one, it just uses the ASCII instead. Pretty cool. Now, the only exception to this rule is if this comes out to be 129, this final number here, that means that not all 8 chunks were used. Maybe only 7 chunks were used, and the 8th one is unnecessary. It can be an 129, which means don't worry about this chunk or any chunk beyond it. So now you bet you're wondering, what about, you know, chunk 9 through 18? Well, those are the error correction chunks. Or for maybe if it has that, you know, 129 end chunk on it, then those could also be padding as well, because each one of these data matrices actually has a max size to it. Now here's this great PDF that my buddy Sean found for me. It has a whole bunch of similar information in it, and I'll link to this PDF in the comments. It's on the internet. But it will tell you each size here, and you probably have to see if I can't. There we go. So if I have, in my case, an instance of 14 by 14 data matrix, I have 8 chunks of code word. So I have my 8 chunks, and then I have 10, that's the other 9 through 18, I have my other 10 error correction words, which I'm not probably ever going to bother to learn. So it gives you a little more data. It's like it can hold 16 numeric total, or 10 alpha numeric in total. And so 14 by 14 is actually a 12 by 12 because the pattern, I guess, doesn't truly count. You don't really take that into effect. And so this will tell you how many you have. So if you're working with a 14 by 14, you have 8 chunks of data to work with, and this is very important to know, or else you're going to run over into the error correction stuff and you're going to get this weird data and you'll be like, what the crap is this? So I'll link to this in the comments. You can probably find this. I didn't see this on Wikipedia anywhere, but Wikipedia is also another great resource to how to figure this out. So if you come up here right below this great graphic representation they give here, is the thing I was talking about earlier, whereas 1 through 128 is the ASCII value plus 1, 129 is an end of message, and 130 through 229 is the digit pairs. Now the rest of the stuff, I haven't really seen this used, but they reference a little bit more of that down here as well, and how to use that if need be. So there you are. That in a nutshell is how to solve for a data matrix. Oh yeah, look at this. They give a great little picture here to kind of show purple being the pattern defined, green being the actual data chunks that you'll be decoding by hand, and then yellow if it has need be for padding. You can see right here, this yellow in particular has the dots down here at the bottom and the dot down here up at the top left. Talking too fast for my own brain to keep up. This is the classic 129. This is 128 and this is 1, so therefore 129, and this means end byte. So therefore these are just simply padding to fill out for padding. I mean, that's really all there is to it. And then all these reds are all your data correction crap. Now also to note, in this case, this let's see, 2, 4, 6, 8, 10, 12, 14, 16. This is a 16 by 16. It has 4 extra little bits here. Those are just completely unused. And this is, to note here, this is a different case because it's a different size for the corner byte, as it's called. This is a sideways L, and it has its remaining 3 bits here stashed to the side. That would be case number 2. So there you are. So that's how you know where the bits are for that special case. And Wikipedia shows they have a barcode. That same barcode here. They show how it's spelling Wikipedia for you, and where all the error correction is, and where the wraparound pieces are here as well. You can see the D here is wrapped with the D over here. The I up here is wrapped with the I down here. and the I down here is wrapped with the I up there. The W here is the W over there. So Wikipedia, a great reference for this if you want to learn more. I plan on doing some more example videos with different sizes. I'll probably do 10 and 12. So when and if I do those will be linked in the comments. So I hope this is a good reference to learn DataMatrix, and I hope you either take this up as a fun puzzle for decoding data matrices, as I wanted to do with it, or you create the next awesome data matrix reading program. So best of luck to you on either way. Have fun with that.